Hello, my name is Sebastian Gebert. I'm an early stage researcher, and in this video I'd like to explain my part in the TeraApps project. The project itself is focused on Terahertz applications and is funded by the European Union under the Horizon 2020 program. For my studies I moved from Germany to France, where I work at the University of Montpellier. The main goal of my work is the development of Terahertz detectors and emitters based on ultra-fast 2D systems. One way of doing so is by studying phenomena that have been observed in other materials, but had not been studied in the selected systems. Such a phenomena is, for example, the cyclotron resonance emission, which I'd like to explain a bit further. In general, applying an external magnetic field to a solid strongly modifies the system. This leads to the manifestation of direct energy levels, so-called Landau levels. Illuminating the system with the right frequency, an electron can be lifted from a lower to a higher level, which then can be measured as an electrical signal. In short, one can detect light with a matching frequency. Interestingly, it is also possible to use this mechanism in the opposite way, hence not to detect, but to emit light. This works like the following. By applying an electrical pulse, one can excite electrons to a higher level. After a short time, the electron will fall back to a lower level, emitting the energy difference as light. This energy difference, the difference between two Landau levels, is dependent on the external magnetic field. In other words, the magnetic field determines the detected or emitted light. The exact difference also depends on the material itself. An estimation of the cyclotron resonance emission for low temperatures is shown here for 3 different materials. If you have a close look on the graph, you might notice that it requires quite high magnetic fields to tune the emission in gallium arsenide over a few terahertz. As a comparison, the neodymium magnets, which are rather common in everyday life, can only reach up to 1.4 Tesla. An increased tunability has already been found in other materials like in indium antimonide or mercury cadmium telluride, but the search for even better systems is still in progress. Apart from the before mentioned enhancement of known effects, novel 2D systems also harbor completely new phenomena. A very interesting one is the quantum spin Hall effect, which is also known as topological insulator. Classically, we characterize materials as metals or insulators depending on how they conduct electricity. A topological insulator is somehow both. It is insulating in the interior, but conducting on the boundaries. Moreover, the conductance is quantized and spin selective, which is rather unusual. By applying a voltage to a top and a backgate, it is also possible to transfer a topological insulator from a conducting to a non-conducting state. This transition is very similar to the on and off state of a field effect transistor. In fact, a transistor based on a topological phase transition would be an improvement not only to the commonly used field effect transistors in terahertz detection, but transistor-based technologies in general, especially in our mobile devices and continuous development towards more powerful and efficient processors. For all mentioned scenarios, it is essential to design, fabricate and characterize working devices. Most of my work is dedicated to the characterization and testing, but I'm also involved in the design and fabrication either at the University of Montpellier or in close cooperation with partners inside the TeraApps project. I hope you enjoyed the video and don't forget to subscribe to our channel if you'd like to know more about the TeraApps project and the work done by other early stage researchers.